Now we're going to talk about non-integers, that is fixed and floating point numbers which allow us to represent fractional values. So in decimal we use a decimal point to represent fractional values. Here we have 12.25, which we can express as 1 times 10 to the first plus 2 times 10 to the 0 plus 2 times 10 to the minus 1 plus 5 times 10 to the minus 2. In binary we use a binary point or radix point to do the same thing. So 12.25 is going to be 1100.01, and you can see how that's built up here. This is what fixed point numbers are, or fixed point arithmetic. We have a binary point that we choose somewhere in our number, and we use that to decide what the interpretation of each of the places in the numbers are. So here we have 0.011.110, which is 3.75. Now the real question is, where do we put this binary point? After all, we just have 6 bits, we could put the binary point anywhere. For example, we could put it right in the middle. So if we have 6 bits and we put the binary point in the middle, we can go from a maximum number of 7.875 down to a minimum number of 0.125. But if we put it further to the right, now we can have a larger maximum number, 63.5, but we have a much larger smaller number of 0.5. Or we could put it all the way over on the left, and now we have a much smaller maximum number, less than 2, but our minimum value is now much smaller. So we can move the binary point around and we can decide where to put it to get the number range we want. In fixed point, math is almost the same. So addition just works the way you'd expect. No problems there. You just need to remember where the binary point is. Multiplication is a little bit different. So when you multiply, you go through and do the same thing you did before, but now you have to figure out where to put the binary point, and you have to do some rounding. So we put the binary point in the middle, we chop off the extra bits at the top, then we need to round the lower bits in order to give us our correct value. So multiplication is a little harder. But there's a problem with fixed point numbers. And the problem is that it only works if we know the range. So we need to know what kind of numbers we expect to display, or we expect to need to use, so that we can choose where to put the binary point. So if we know the numbers range from 16 to plus 16 to minus 16, or 1.5 to 0, we can choose a reasonable binary point. This is actually surprisingly common. So digital signal processing, so the processing that goes on in your cell phone to communicate with the cell phone tower, those places know what sort of signals to expect and what the ranges are going to be, so they can optimize to use fixed point. But usually we don't know this, and that poses a problem. So the solution to this is floating point numbers. And this is pretty simple basically. We're going to use some of our bits to choose where the binary point goes, and then we're going to use the rest of the bits to express the number. So say we have 20 bits, and we're going to use 4 of those bits to specify the binary point. Here are 20 bits. We get 16 of them to specify our number and 4 for specifying where the binary point goes. So if we specify the binary points at position 12, we end up with a number like this, where we can display we can record very small numbers but not very large numbers. Or if we put in a smaller number for x in the right-hand side, maybe we can have larger numbers but less precision. So what the floating point allows you to do is use some of your bits to specify where the fixed point number goes. So we're going to use some of our bits to choose the binary point. This allows us to have large or small numbers by moving the binary point. So this is great. We can make more efficient use of the bits. If we need to record very small numbers, we can do that with high precision by moving the binary point. And if we need very large numbers, we can get a very large range of them by moving the binary point in the other direction. So here's a floating point number. This is what it looks like, and we're going to talk about what the different parts are. So they start off with a sign bit. So we're going to have a bit which indicates whether it's positive or negative. Then there are the significant digits. This determines the precision. How many bits we have here determines how accurately we can represent numbers. This is known as the mantissa, or the fraction of the number. We then have a base, which is typically an implied base. That is, we don't store the base in the number, but everybody agrees that the base is going to be 2. And finally, we have an exponent. This is the part that allows us to move the binary point. When we take the mantissa and we multiply it by 2 to the something, that's the same thing as moving the binary point left or right. So let's talk a little bit about the IEEE floating point standard. So this was developed in about 1980, and the idea was to standardize floating point math. This makes it portable and maximizes quality. So before this standard, floating point numbers on one computer might be totally different from floating point numbers on another computer, and that made it very hard to move data and move programs back and forth. So here's what a 32-bit IEEE float looks like. We have 32 bits. The most significant bit is the sign. We then have 8 bits of an exponent and 23 bits of mantissa or fraction. And here's the interpretation. Minus 1 to the s, so that's the sign bit. If s is 1, it's going to be negative, times 1 point f. So you've got this 1 before f, times 2 to the e minus 127. So this is not at all obvious. It looks sort of like what we talked about before, but there are some weird things going on here. So this implied 1 is normalizing the numbers. It helps make sure there's only one representation of each number, and we'll see that in a minute. The exponent has a bias here. This makes comparisons easier, and it means that we don't have to support negative numbers in the exponent because we know we're always going to subtract 127 from it. So these sorts of standards are really hard to get right. This looks like a weird standard, and it is a little bit weird, but this is something that takes a long time for people to work out. And it's taken so long that, for example, graphics processors only agreed to standardized number representations in 2008. So this has been a long time coming, even for processors these days. So let's talk a little bit about floating point details, and then we'll go into some examples. So here's our floating point number, and here's its representation. The sign bit s, this tells the whole number. If it's 0, the whole number is positive. If it's 1, it's negative. The exponent e, this is an unsigned value, but we bias it by minus 127. That means if the exponent is 128, we end up with a value of times 2 to the 1, because we subtract 127. By having this bias, it makes comparisons very easy. The fraction is an unsigned value, and it's just a binary number with the binary point to the left of the most significant bit. If we want to move the binary point for the whole number, we use the exponent.